So then we have, are happy to have as a first speaker Jens Niemeyer from the University of Göttingen. We'll talk about structure formation, gravitational structure formation with scalar fields. So the floor is yours.
Thanks a lot, and thanks for the invitation. I think like many previous speakers, we'd all be happier to be in Russia, and maybe we can make this happen at some point. But I'm glad to be here. It's been really interesting so far. I've changed the title a little bit because if it's gravitational structure formation, then it's obviously non-relativistic, and I'm only going to talk about gravitational structure formation. So basically, throughout the talk, I'm going to ignore all non-gravitational interactions. This is also on purpose. This is not a talk entirely about dark matter, because at the end I will take the liberty to deviate slightly from dark matter and talk about the very early universe. Much of the work that I'm going to present is actually work by Bodo and Benedikt, and some of their unpublished work as well. Bodo Schwabe used to be a student and a postdoc in Göttingen, and now is at University of Zaragoza, at least virtually, soon physically, I suppose. And Benedikt is a student at Göttingen. So let me start with this slightly busy slide. So I'll spend a few minutes on this with an overview of some aspects of axion dark matter phenomenology. And I think this is actually the very interesting and fascinating aspect of this field to me, is that you have this very rich and wonderfully interesting phenomenology of and physics with only one free parameter, namely the axion mass. And you get all kinds of different phenomena that have similarities to other fields of dark matter, depending on which aspect you're looking at. So for instance, starting with ultralight axions, or as they're often called, fuzzy dark matter, according to Hu and friends. So FDM is what I'm going to use here as well. In this case, you have three different aspects with three slightly different ways of finding constraints on the axion mass. One is essentially a linear effect, and that's the suppression of small-scale perturbations in the transfer function, which I've called WDM, like warm dark matter. Like it's very similar in methodology and phenomenology to warm dark matter or sterile neutrinos, where there is a cutoff and in the small scale, at the small scales in the initial power spectrum. And therefore, also the kinds of constraints, cosmological observational constraints that you get on the axion mass from this angle are nearly identical to those that have already been found for warm dark matter or sterile neutrinos. For instance, from high redshift luminosity function, galaxy luminosity functions, or reionization, or the Lyman alpha forest. And all of their systematics also apply to fuzzy dark matter. And indeed, the Lyman alpha forest, if you take this at face value, gives you a lower bound on the axion mass for ultralight axion dark matter, for if the totality of dark matter is made of these ultralight axions, of about 10 to the 20 eV. So this is already in conflict with explaining dwarf galaxy cores with solitonic cores made of ultralight axions, for which you would need masses of the order of 10 to the minus 22 eV. All right, so there's a kind of a conflict here as well. So let me just state this right out front. There is a need for clarification. This is consistent with other constraints based on this linear physics from the suppression of small scale perturbations. I'm not going to talk at all about this because I'm going to focus mostly on the nonlinear physics and also on simulations of nonlinear effects in halos. So just keep this bound in mind here. Now, but moving on to these nonlinear virialized structures, there is an effect that has become very prominent, and that is the formation of solitonic halo cores. These are essentially boson stars on the scales of kiloparsecs in the case of ultralight axions. These boson stars come in all sizes and flavors because the Schrödinger-Poisson equations have a scaling symmetry, and once you've seen one, you've seen them all, kind of, because you can take the same solutions of the stationary Schrödinger equations and then apply them either to halo cores for fuzzy dark matter, or to QCD axion stars in axion mini clusters, or even to the very early universe, as I will at the end. But once these form, of course, you may use them to explain small scale effects in dwarf galaxy cores, and that has been done extensively. And I'll show a few results about this. But then I think perhaps even more interesting. So, by the way, since this is about cores, I've called this similar to self-interacting dark matter, which is another variant of standard cold dark matter, to potentially explain the existence of halo cores. So you get this kind of flavor, and then the final flavor is an enhancement of gravitational fluctuations in halos above the usual CDM one, caused by interference patterns. So these interference patterns you can think of as giving you a shot noise on the scale of the de Broglie wavelength. So their typical scale is de Broglie wavelength scale, which of course grows with sinking axion masses. So this shot noise importance becomes greater as you go to lower axion masses, right? So at some point, there are gravitational relaxation or gravitational heating effects that are in many ways similar to those that you'd expect from machos. So the kinds of constraints here are very similar to those that people have used to constrain primordial black holes, for instance, right? So you get all these kinds of different effects from just a single scalar field with a single parameter, namely the mass, and I find that interesting. Okay, so that's ultralight axions, and I will talk a little bit more about those bottom two ones, the nonlinear ones, not so much about this top one. And then, of course, there's QCD axions that we've already heard about, where the wave-like effects are generally not so important on the scale of structure formation, but of course become important for the formation of axion stars. But the initial conditions may be very different, with very strong small scale isocurvature perturbations in the initial conditions, which give rise to the formation of axion mini clusters that, of course, Igor and others have worked on a lot in this pioneering work in the 90s, which is crucial to know for direct and indirect detection experiments for QCD axions. And then finally, of course, even also in these scenarios, you predict the formation of these solitonic objects, which in this case, they would be called axion stars. Okay, so that's my broad overview over axion dark matter, and I will mostly concentrate here on simulations and nonlinear effects. So just a quick overview on of the scales that we need to pay attention to. First of all, I'm talking about phases where axions can be considered cold and therefore non-relativistic, and therefore they can be described by the Schrödinger-Poisson equations, so just your standard Schrödinger equation coupled to its own self-gravity. And we know that, and we've known that for a long time, that on large enough scales, gravitational interacting waves are equivalent to collisionless matter. There is a kinetic regime for weakly interacting waves, just like there is for particles, and therefore their gravitational dynamics becomes indistinguishable on large enough scales. So what are these scales? Once we're above these scales, once we're in the regime where things are purely kinetic, we don't need to worry about wave-like effects. So what is the boundary? Where do we need to start thinking about wave-like effects? One way, there are many ways of motivating this, but one way is to go into the fluid formulation by modeling transformation, where you can write the Schrödinger equations in terms of a continuity equation and an Euler equation, where you get this quantum or Bohm potential or sometimes also called quantum pressure term, which I don't like so much because it's neither quantum nor pressure. It's basically just the scalar gradient energy hidden in this term. But then what you can do, and at least to me, this is a way of motivating the scales that we need to keep in mind, is to define a sort of quantum Reynolds number. Again, a bit of a misnomer, but just to coin a name here, by comparing the nonlinear advective term, not in this case to the viscous term, but to the quantum pressure term. So dividing those two gives you the de Broglie wavelength over a typical length scale, which could be, say, the virial radius of a halo, right? So if this becomes large, say order unity, or if whatever length scales you're interested in are similar to the de Broglie wavelength, then we need to worry about these effects controlled by Q. And similarly, there's a time scale, the gravitational relaxation time, which controls those fluctuating or controls effects caused by the fluctuating gravitational field. And I've seen this first spelled out in Levkov, Panin, and Kotchev's paper, where they've written this in this very nice intuitive form, that this relaxation time is some coefficient times again this ratio of de Broglie wavelength over your integral length scale to the power of -3 times the crossing time, R over V. So again, everything is controlled by this ratio. And if you're interested in phenomena that have this controlling parameter not very small, then you need to worry about wave-like effects. If this parameter is very small, you can do whatever you're used to doing with CDN, okay? And the same is true for simulation. So if this parameter is very small, then you can happily use your Nbody methods without getting any problems, as long as you use proper initial conditions. So, all right, so now first part, I'm going to just talk about ultralight axions. What the things I said before are of course true for all cases. You've seen this plot before by Kenichi Saikawa, I think originally. So I'm talking about the case where we start with a uniform initial field, ultralight axion dark matter field without any small scale perturbations. And here in this case, just to give you a guidance for the scale here, the de Broglie wavelength, or de Broglie wavelength divided by 2 pi, is of the order of kiloparsecs for masses around 10 to the minus 22 eV. So this is why this mass range is so interesting for ultralight axions, right? Because then you're getting into the region interesting for galaxy dynamics. So here's one more motivation. This is a paper that Dottie Marsh and I wrote 2 years ago, taking one particular example, the ultra-faint dwarf Eridanus 2, which has a, so this is a dwarf galaxy, satellite galaxy in the outskirts of the Milky Way, roughly at the virial radius of the Milky Way. And it has a compact old stellar cluster slightly off-center, right? And the existence of this star cluster already gives us clues about the nature of dark matter. And indeed, this was already used to constrain primordial black hole masses. And like I said, the methods are nearly identical. So if you can use it for primordial black holes, if it's based on gravitational heating, you can also use it for ultralight axions. And that's just what we did. And you can look at the expected number of subhalos and find that you get constraints on the mass, which would put you above 10 to the minus 21 EV, just based on this simple estimate of whether you'd even find a subhalo with this mass. But then you can look at gravitational heating, and here you find that you get strong constraints, for instance, between masses of 10 to the minus 20 and 10 to the minus 19 electron volts. So assuming that we accept the Lyman alpha force bounds, which puts us to the right of 10 to the minus 20 EV, these bounds then tell us that we cannot have ultralight axions all the way down to almost 10 to the minus 19 EV. where we're getting very close to the bounds from black hole superradiance by supermassive black holes. All right, so we're getting closer to closing the window, but this comes with many uncertainties and caveats and involves some approximations that we had to make. So there are many uncertainties, and I use this as a motivation to do simulations. We need more realistic full numerical simulations of problems like this one, because this is important to get into this region for constraining masses above 10 to the minus 20 eV. Okay, so moving on to simulations. Now, hoping that I've convinced you that we need to do better simulations. What kinds of methods are there? So as I said, if you're interested mostly on linear scales or those affected by the transfer function, for instance, for constraints from the Lyman alpha forest or high Z luminosity functions, etc., or in Axion mini cluster formation, then you're very well off with using standard Nbody methods with modified initial conditions, right? And that's what people do. And it's been shown many times that this is a pretty good approximation as long as this controlling parameter lambda over r is small enough. You can also use the modeling or fluid formulation directly, and some people still do. We've also tried this and found it not very satisfactory because these quantum pressure effects are hard to model, and the resolution requirements and validity of the model is not yet clear, and maybe there is no region where this really makes a lot of sense. So we're not doing this anymore. Then you can do the brute force approach and solve the Schrödinger-Poisson equation explicitly on your grid, either with spectral methods or finite difference methods. This is something you probably have to do if you want to get the full wave-like dynamics covered. So in the end, I would now claim that there is no way around explicitly solving the Schrödinger equation, at least on some scales. So this is useful by numerical constraints for isolated halos or small cosmological boxes, or if you have a really big cluster all for yourself. So if you're really rich or lucky, you can do this for medium-sized cosmological boxes, but it's impossible, say, to do something like illustrious for fuzzy dark matter in the range of 10 to the minus 21 or so eV. It's simply not doable. So that is why we've created a hybrid method, which is based on an adaptive mesh refinement approach, and where you solve the Nbody dynamics on the coarse grid scales, motivated by this Vlasov-Schrödinger correspondence, and then only solve the Schrödinger equation on the finest grid. And I'm going to show you some results of these two methods here, basically. All right, so some of the things I'm going to show is just solving the Schrödinger equation, and some of it will involve this hybrid method, which you can then use for zoom-in simulations in big boxes. So then you can take your standard cosmological boxes, but if you're only interested in, say, samples of halos and you want to study their detailed dynamics, then you can use this zoom-in hybrid method. Okay, so our code, which is also public, is called Axionix. It's based on the Nix cosmology code. And it has fuzzy dark matter, or Schrödinger dark matter, cold dark matter in the form of an Nbody formulation, and the hydro equations. You can download it, use it, play with it. The public version doesn't have the hybrid method in it yet, but might have in the future. So here's just an illustration of the adaptive mesh capacity here, showing a spherical collapse problem, starting with scales of hundreds of kiloparsecs and then zooming in across 6 levels of refinement down to refinement of sub-kiloparsecs. So that, of course, is pretty much standard for AMR, but here we do this for the Schrödinger equation. This we've analyzed, and you can look, for instance, at the velocity distributions of, so this is by the way, this is for mixed dark matter simulations. So using the Nbody solver for something that behaves like cold dark matter. For instance, you can think of this as a scenario with several axion-like particles, some of them light enough to be described by the Schrödinger equation, and perhaps another species that is, in this case, described by cold dark matter, formulation. Not too uncommon in, say, string theory scenarios that you have multiple of these fields. So you find these velocity distributions for each component, and as your ratio of cold dark matter to no, this is fuzzy dark matter to cold dark matter increases. So this is all fuzzy dark matter. Then of course these curves all overlap, and the velocity distribution of the fuzzy dark matter, as you would expect on average, is well described by a Maxwell distribution. Here on the right, you can see the formation of these core solitons, which also form as if you only have a tenth of dark matter in fuzzy dark matter, you still get a soliton, but it barely shows up in the total density profile. But then it starts, peaking up, rearing its head out of the general density distribution, and then you get this classical solitonic profile for pure fuzzy dark matter, as you would expect. Okay, where on the outside everything is just like usual, and the ratio is just given by the initial ratio of fuzzy and cold dark matter. All right, now on to this hybrid method, which is still under development. We've already used it for publications, but it's still being improved. And here's a summary of a recent improvement that Bodo Schwabe has implemented and worked on. So basically what we do is we use adaptive mesh refinement, so a hierarchy of grids, where we use a particle method, Nbody method, on the low resolution levels, motivated by the Vlasov-Schrödinger equivalence, and then a finite difference scheme for solving the Schrödinger equation explicitly on the finest level, on the most refined level. And of course, the crucial question is, how do you treat the boundary of these different regions? So if you have particle dark matter flowing into this Schrödinger region, then you have to convert particles into scalar field, and this is done using what is called the Gaussian beam method, which is also used in quantum chemistry, where particles in some intermediate region are represented, or the field is represented by a Lagrangian distribution of Gauss-shaped beams, Gaussian-shaped beams with their own phase that is evolved according to the Schrödinger equation. Okay, so those are overlapping Gauss beams, which are then used to reconstruct by the sum the wave function in the Schrödinger formulation. Okay, so what Bodo is working on right now is a comparison to a big comparison project, which is called Gora, has been around for 5 years now, which is a code comparison project for galaxy evolution simulations involving many different simulation groups. And their flagship paper, which came out in 2014, has a proof of concept halo, as they call it, of 1.7 times 10 to the 11 solar masses. So this is a bit higher than the standard dwarf galaxy masses that people usually use for fuzzy dark matter simulations. But it's extremely well studied. And our goal was to take their initial conditions, convert them exactly into those for fuzzy dark matter by changing the transfer function using the same random seed as all of these groups have used for the same halo, and rerun the same halo after checking that our code reproduces well enough the original results if run with pure cold dark matter, which Bodo has done. So these are the initial conditions now with fuzzy dark matter. And then on the small scale, zooming into the halo, he has reconstructed the Schrödinger field using the Gaussian beam reconstruction with a total of 11 refinement levels all the way down now. here into the very center of the halo, and you can actually see the soliton forming here as you'd expect, and as we would generally now know happens in these fuzzy dark matter halos. And again, you can compare the velocity distributions with a Maxwell distribution, and this is now the Gora flagship halo in fuzzy dark matter. And lo and behold, it does form a soliton pretty much like you'd expect. Now, this is of course work in progress. We hope that we can extend this with hydro simulations and star formation and feedback, and then have a very well-defined in detail comparison between a fuzzy dark matter galaxy and the corresponding CDM galaxy in order to validate and to understand the systematics of these fuzzy dark matter simulations, which is something that has been lacking so far, I think. Okay, so that's it for these fuzzy dark matter halos. Let me move on a little bit to the QCD axions. And again, you've seen this plot before here. The fun is all in the initial conditions, which need to be derived from a post-inflationary Cauchy-Quinn symmetry restoration and breaking, which then gives rise to these patches of uncorrelated phases and therefore axion densities that can have very large local isocurvature fluctuations. Okay, so I'm just flashing this up because I expect that Javier Redondo is going to talk more about this in the next talk. There have been very high resolution, high quality simulations of the early universe evolution of the axion field from PQ symmetry breaking all the way through the QCD phase transition, showing the formation of strings and domain walls and their decay, ending in this final state, which is very inhomogeneous on small scales. And then we've taken those and transferred those into an Nbody simulation. And here I'm pointing to David Ellis's talk later this morning on the formation of axion mini clusters. And what we've done is taking these initial conditions together with Klaus Dolak in Munich, then run a big Nbody simulation of the evolution of these perturbations, which give rise to the formation of axion mini clusters and their merger into axion mini cluster halos. So there's structure formation on small scales, and small scales meaning that the co-moving length of this box is less than a parsec. So I've called this the small box simulation challenge part 1, because you would think that this is a small box, but you ain't seen nothing yet. So if you think this is small, then wait for a few more minutes. All right, so this is what this looks like. The results are potentially interesting to direct and indirect detection experiments. More on this in the following talks. You can measure the fraction of axions bound into halos. You can measure the number of mini clusters and the halo mass function, which before equality shows this pronounced peak at the mass of 10 to the minus 13 or so solar masses, which are the classical mini clusters, and then they're merging into a power law distribution of halos, and more on this in the following talks. But then you can also take these initial conditions and further zoom into the core of these mini clusters, and that's what Benedikt Eggermeier did as well, now using the Schrödinger equation, and so he studied the small scale evolution of these perturbations. And of course, as you'd expect, you find the formation of these axion stars. The axion stars are excited. They ring like a bell. They're actually quite a nice bell with, with two harmonics that we identified here. And their mass grows in agreement with previous results by Dima Levkov and others in their paper. So the initial growth of these axion stars follows the square root of T law. And then we've speculated in this paper that this should slow down at a certain point, namely at the point where this condensation time which is dependent on the velocity of the waves which condense, becomes dominated by the virial velocity of the Axion star itself. So it's no longer just given by the environment, but by the atmosphere, if you will, of waves around the Axion star. And that gives you exactly the mass that was already found by Shiwe et al. For solitonic cores. It essentially corresponds to the Axion star having the virial temperature of its host halo. So we predicted that this would then produce a turnover in the growth to much slower growth. And in fact, we think that we can confirm this now with simulations by Jiajun Chen, a former PhD student in Göttingen, whose simulations seem to show this turnover from square root law to a 1/8 law after reaching this mass bound. Okay, so this is hopefully also something that we will continue to understand better in the future. You know, how do the masses of these Axion stars evolve with time? Okay, and then
just for your info now, 30 minutes have passed.
Okay, I'm almost at the end. Okay,
okay,
so,
good. Yes.
so I'm almost at the beginning, because now I'm going back to inflation. So I'm working my way back in time, but just a few words about this. So this is the small box simulation challenge part 2, and now we've reached box sizes of 10 to the minus 20 meters. So that's going to be hard to beat. We call this the biggest simulation of the smallest piece of the universe. And this is now early matter domination that we've already heard about in Chris's talk yesterday, for instance, with implications for primordial black hole formation and primordial gravitational wave production. So as was already shown by the Auckland group, Nathan Musoki and Richard Easter and others, the Schrödinger-Poisson equations work in this post-inflationary early matter domination. So this is for inflaton potentials with an m square phi square bottom, really, that then if reheating takes sufficiently long, is sufficiently late, gives rise to this matter-dominated epoch. And so in this matter-dominated epoch, the only difference to standard structure formation is the initial conditions again. So if you put in a realistic power spectrum, you can run an Nbody simulation, which this is. So this is what Benedict simulated. And you find inflaton clusters with halo mass functions that can be predicted by Press-Schechter formulation or by a slightly more sophisticated model like the peak patch model for halos. And then both of those pretty much confirm the Nbody simulations. All of these have systematics which sort of compensate each other, but we're now confident that we can robustly predict the halo mass functions of these inflaton halos right after inflation. So this is about 20 e-foldings after inflation. Okay, so this is in pretty good agreement. And again, of course, lo and behold, you can zoom into these halos now using this hybrid method again. Not exactly the Gaussian beam method, slightly different boundary conditions, but essentially the same idea. And that's what Benedict works on right now. And again, of course, as you'd expect, because you're solving the same equations, you form these central solitons, which we now started calling inflaton stars. So we form inflaton stars with masses of micrograms. Okay, so we have a 10 to the minus 20 meter box, and we have gram-sized and below objects in there. So that's kind of fun. And lo and behold, their properties are similar to Axion stars if you rescale them properly, and their mass growth again is determined by the condensation time, and you find them ringing with their quasi-normal mode. Okay, so all of this hangs together, and it's really interesting and fun because you can use whatever you've learned on very large scales, the largest scales, cosmological scales, all the way down to the very smallest scales that we would expect structures to form. All right, so that I think is fascinating all by itself. Okay, so let me close with some random final thoughts. There's been a lot of activity on the physics of these boson star soliton solutions. I think we have a broad understanding now of their formation. by condensation. Thanks, of course, also to work by Igor and his group. We still have some open questions, of course, like are there multiple solitons in a halo? Are they really condensation events, or are they just remnants of the initial cold temperature of those halos, which I now think is a better description? Are those oscillations important for observations, etc.? The granules appear to me to be more interesting now for future observational constraints than those solitons by themselves, because they are largely unexplored, both theoretically and observationally, and similar to macho constraints. So I think there's a lot to do here as well. And then finally, I've already pointed out that fuzzy dark matter, ultralight axions, are sort of an endangered dark matter species because the window is starting to close. But don't despair. If you've started to work on this, you can always retrain and work on smaller scale stuff as well, because it's essentially the same physics applied to different times in the universe. And I'll close with this happy thought. Thanks very much.
So, thank you, Jens. Thank you very much for this exciting talk. So the floor is open for questions. We have about 4 or 5 minutes left. So Igor, you are the first.
Yeah, Jens. Thank you for the very nice presentation. These inflaton stars, are your main motivation to find out how many primordial black holes can be formed? No?
Yes, and now I stopped my presentation here.
Also, do you study this with preheating or?
So far, we've only studied this in an Nbody simulation. Wait, let me.
So it's just normal adiabatic then. So
far, the only inflationary information that we put in is assuming that there is an m² phi square bottom of the potential. Okay, we haven't put in any, and that essentially determines the initial power spectrum, which is a slow roll power spectrum on super horizon scales, and then it drops like k to the -5 on sub horizon scales, and that's just very robustly what you get at the end of inflation. And then we assume that the further evolution is matter dominated. That's really all we put in. Now so far we haven't put in any coupling, self-couplings, field self-couplings, or coupling to other fields. So we haven't done any of the other fun physics that we might be doing. And of course, it is in principle interesting for primordial black hole formation. We're looking at this, and gravitational waves. Yes, but
you are thinking to include effects from preheating, possibly, or something.
Yes, possibly, and that's another extension that that we're looking into. But it's not in this simulation. This is not accounted for. This is just taking in a transfer function that you naively expect. No enhancement of perturbations by preheating.
Valerie, you had also a question.
Well, actually, it was basically answered already, but my question was sort of general. You have these sub-gram stars made of inflaton, and the inflaton is going to decay anyway. So what sort of physics may come out as observable or potentially observable effect of these bosonic, of these inflaton stars?
Maybe not so much of the inflaton stars by themselves, but the entire structure now, of course, allows us to make more quantitative predictions for gravitational waves. So now we can look at the full nonlinear evolution of mergers, for instance, in this structure, and compute the gravitational wave signal, and potentially put this on again. Oops, what am I doing here? And potentially also the formation of primordial black holes. But I think you're absolutely right. The inflaton stars by themselves are going to evaporate and decay at some point, and so all by themselves they probably won't have any observational consequences. But indirectly through mergers and production of gravitational waves, which we can now do in a more quantitative way than previously possible.
Don't you expect that the gravity waves will be extremely short wavelength?
Well, they will be pretty much exactly what people have already estimated in previous work. And, those produced by subhorizon fluctuation, nonlinear fluctuations in early matter domination. So they are short wavelength, but they can be, depending on the epoch, they can be in principle detectable. This is what we've heard yesterday as well. So this is I think pretty much exactly that range of scales that was discussed.
You can also go to low scale inflation to get wavelengths bigger.
So we saw these plots yesterday, and depending on your reheating temperature, these are the kinds of scales that you can reach. This is all the same. It's the same scenario. It's just that with these simulations now, we can actually predict the power spectrum of these gravitational waves, which we still need to do, of course. And whether or not inflaton stars by themselves make a difference there, we have no idea yet. So.
Okay. So I think the time has passed, and so we have to proceed. So let's thank Jens again. And